So start, Yogesh, please start the
Yes, ma'am.
live
Yes, ma'am.
recording.
I'm just starting. Just give me a few seconds
Ma'am,
to
you have
start
done
with
so much of
this.
work in your life.
Now, yes, ma'am.
Reading out your introduction is a task in itself.
Yes, ma'am. We are on live now, and recording is also started.
Started, yeah.
Okay. So I'll start now.
Please go ahead, ma'am.
Welcome everybody. Welcome everybody to this evening of Learning Physics with Conceptual and Problem-Based Approach, organized by the National Academy of Sciences India, NASI Delhi chapter, an 11-week course which started on 27th of July 2020. And right now we are in the 11th week. And today we have with us Professor Annapurni from the University of Delhi. She will be teaching us a solid state physics. Is my second slide visible?
Yes,
yes,
ma'am.
yes, it is visible.
Yeah. So, and followed by her lecture, we shall have another lecture by Dr. Saurav Sood on electromagnetic theory from University of Delhi itself. And now it's a pleasure for me to introduce Professor Annapurni, who is well known to everybody around us, and I think in almost the whole of India. To the audience, probably you have not had the pleasure of listening to her golden voice. So because she has done immense work in her life, me and Dr. Bindal will join together to read her introduction. So Professor Annapurni Subramanian received her PhD in 1990 from Department of Physics, IIT Chennai, entitled Magnetic and Electrical Behavior of Certain Hydrogenated Rare Earth Transition Metal Systems. She completed her postdoc in 1990 from IIT Chennai and another one from National Physical Laboratory, Poosa, New Delhi. In the year 1990 to 93, she started her career from DU as a lecturer from 93 to 96, followed by readership from 96 to 2001. Subsequently, she joined Department of Physics, University of Allahabad, now Prayagraj, for a period of 2001 to 2, and again joined Delhi University back again as a reader and became a professor in 2006 for our benefit. So I say, ma'am, it's for our benefit that you came back here. So she has been engaged in several administrative assignments as a coordinator, MTech Nanoscience and Nanotechnology, Provost, Rajiv Gandhi Hostel for Girls, Managing Committee, Daulat Ram College, Keshav Mahavidyalaya, Lady Irwin College, and Ramlal Anand College, also along with Kirorimal College. Ma'am, Pushpa ma'am, can you please introduce her from the line?
Yeah, sure.
Punita ma'am, can you make it slide mode, presentation mode?
Yeah.
Lower button, yes.
And I cannot see anybody.
She has been chairperson. Oh, what is it? Okay.
GB.
Chairpersons of many GBs of some hostels and colleges, Academic Council, Jawaharlal Nehru University, Pondicherry University, MET Institute of Nanotechnology, Gyan, local coordinator, etc. Under her guidance, 18 students thus completed her PhD, 7 are currently working, and over 70 BSc, MSc, MTech have done dissertation with her. She has 135 international refereed publications, 15 proceedings, and 1 book chapter. She has 11 approved projects under DST, Nano Emission, SERV, CSIR, DU, etc. The list goes on. Obviously, it cannot be completed in 1 or 2 slides. So we are indeed honored to have you here, ma'am, with us. And we have already had the exposure of listening to you many times at our college also. And it is really a privilege. We'll again be able to listen to your talk today. So you're most welcome. And we welcome you from the core of our heart. I request you to kindly start your presentation and share your screen.
Thanks a lot, Pushpa and Punita and Yogesh. It's really nice to come here. I've been waiting for this, but because of other issues, I couldn't come for the lecture. And what I should tell is it is all your wishes and your liking and your motivation that you people motivated me to really do a lot of work. That's what I would tell. With this, let me see how much I'm able to motivate our young students.
We keep getting motivated from you, so maybe today we have been able to
yes.
you a bit.
Right.
Yeah, see, motivation is of both the sides, the listener and the speaker.
Yeah, thank you so much.
Thanks a lot.
Thank you.
I intentionally chose to read out all that could be fit into a single slide, simply to convey to the attendees that sky is the limit. If you really love physics, you can go on and on and on. And a physicist never retires. As long
Yeah,
as
yeah,
the
true.
physicist is
Yes, yes,
on the
true.
planet, as long as you are on the planet,
Yes,
you are always working till your
yes,
last breath.
yes,
And that's the beauty that you all should learn,
Yes,
that there
that's
is no
Actually,
limit
yeah.
to where you can go.
actually, we get programmed like that, you know. We can't help it.
Yeah,
yes,
that's
ma'am.
true. Being in
Yes,
RNs or else you don't feel happy at all, you know. The day
Ma'am,
goes
please
bad.
share the
The day
screen.
goes
yes,
bad.
Please
Yeah.
Yeah,
share
yeah,
the screen, and I
yeah.
request you
Yes, yes.
sometime to think of a whole series of either nanoscience or solid state, and we would
Hmm.
willingly sit and
Yeah,
organize it for the benefit of the
Yeah.
sure,
students. Thank you so much.
sure. Yeah. Are you able to see?
Not yet, ma'am.
Hello?
Not yet, ma'am.
Not
Once
yet.
again.
Not yet. Oh. I'm not able to see your. Yeah.
So once you start sharing, you'll not be able to see anything. If there is any question on the chat box, Yogesh will read it out for you.
I think it should come now. Now it. I
Yeah,
able
yeah.
to see
yes,
Now
now?
we
ma'am.
can see.
Okay.
We
Yes,
can
Yes,
yes.
yes,
see
yes,
now.
ma'am. It's there. It's
Now it
there.
is visible.
Okay.
So, ma'am, you'll keep your video off during the lecture.
Yeah, that's what I would prefer.
Okay.
If you
Okay,
want, you
okay,
can
okay. As
have
you
it. No
like,
issue
as you
also.
like, as you
Okay.
like, ma'am.
No,
It's
no,
not a problem.
I have no issue. I can have it. Yes. My video is on now or off?
It's off, off.
It's off right now. You're not visible.
Yeah,
So,
it's off. Is it okay? Okay.
ma'am, you're.
I'm not visible. Okay. Uh, yes. Are you able to see the slides? That's important.
Yes,
And
ma'am. The
slides are
slides are
visible, but
fine.
Hello.
yeah,
Slides are fine, ma'am. Slides are fine. Only your video is off.
My video is off because I'm writing it on an iPad. So I just keep it flat, you know.
Okay, okay. Leave it,
okay.
ma'am. Leave it. Let's have the
Yeah.
lecture first. Yes,
Yeah.
ma'am.
Okay. Yeah. Today, what I was thinking was I will talk about this the theory of metals. All of you all must have heard earlier the concept of Drude's model. The question is, what is it that has changed as you're going from the Drude's model to the Sommerfeld? And what was the reason that one has to go for a different model is important. See, as far as metals are concerned, all of us, we know that we are only worried about looking at the transport because we know they are highly conducting. They have high density of electrons which are present. And we always talk about a transport mechanism in the case of a metal. The question would be, was Drude's model sufficient or insufficient to really explain? So what I have done is I have put a flow here. You can see the flow as recap of the Drude's model. And what you will see, the Drude's model was completely based on a classical statistics. And though it could explain some of the transport phenomena of metal, what you would see is that many properties were not explainable using the Drude's model. And in fact, there were some results which are not matching with the experimental results, and one had to take a back seat and then look at what was wrong with the statistics that we were doing. So then came the Sommerfeld model, wherein classical statistics, and one went into an assumption of still a free electron for the case of a metal, coupled it with the quantum statistics, namely the Fermi-Dirac distribution function, and one had to look at what are the energy levels which are available and how do you fill all these electrons in these energy levels. So from there we move on to the density of states. Look at what are the important parameters that we can get from understanding these density of states, and then we go to the problems. Okay. So some set of problems where we are going to use all the parameters the important parameters which are mentioned, we'll use those parameters and then see how is it we can solve these problems. So just to get into a recap of the Drude's model, okay, I would like to show this. What was the basic assumption? The assumption was, as we all know, that in the case of a Drude's model, what we did was we tried to look at these electrons which are going to move as sea of electrons. Basically, the way you're going to look at the gas molecules moving in a room, you're looking at the electrons, especially the valence electrons, which are moving around freely in a metal. Okay. So here what you have seen is treat them as a gas of conduction electrons. That's what I said, an ideal gas equation is what you talk about, or the kinetic theory of gas. Moving in a background of heavy ions, because you're going to have some sort of ions which are going to be present here, and the electrons are going to move throughout. Okay. Are there electron collisions? What was neglected was the electron-electron collision, as well as the collision of the electrons with the ions was also neglected in this case. So what you call it as an independent electron approximation and a free electron approximation. So what is the probability of these collision? The probability will be 1 by tau, where tau you have seen is the relaxation time. Okay, I'm sure all of you all must have done in the Drude's model. I think Dr. Senthil has done this. But what about the electron velocity? When you're talking about the motion of the electrons, immediately what comes to your mind is what is the velocity which the electrons are moving? What you will see is you are simply using a Maxwell-Boltzmann distribution function in the case of a Drude's model. Now, was this sufficient for me? Yes. Your DC electrical conductivity was very well understood using the Drude's model. As you see here, this you must have done again. Sigma is n squared tau by m, where n is going to be the electron density. So in a problem, when you have to determine the conductivity of a metal, given the value of the relaxation time tau, what you can see is if I know the Avogadro number, if I know the density of the material, the metal that I'm using, and if I know Z, Z is going to be the valency of the metal here and the atomic mass, you should be able to calculate the conductivity of a metal. Was this the same as what was experimentally observed is the question. There did seem to be a bit of a deviation from this, but as far as DC electrical conductivity of a metal is concerned at room temperature, it did explain quite well. But from there, we also found what is the mean free path, which is going to be the distance between the electron collision that is also going to play a role. So what we talk about is the average distance an electron travels between collision is your mean free path, which is of fundamental importance when you're going to talk about the transport in metals. So with all this done, why were we unhappy with the Drude's model still? The reason being the temperature dependence of conductivity was not explained very well here. My relaxation time tau, because you know, if I'm going to plot conductivity as a function of temperature, what is going to happen? My conductivity as my temperature increases is going to go down in the case of a metal. Okay, now right now we are not talking about semiconductor, which is going to give an opposite one. In the case of a metal, you see the conductivity goes down, and we know the reason now. The reason being, as your temperature is increasing, what you're going to have is there's a variation in your relaxation time tau, and this is going to change the conductivity. Okay, so the temperature dependence was not explained using this model. The next thing that we were happy about is the Hall effect. The Drude's model, suppose that if I'm going to apply an electric field, what is going to happen to the electrons is there is going to be a deviation. So as a result, I can determine what is called as a Hall coefficient, which is 1 by Ne. What is N? N is nothing but the concentration of the electrons present in a metal. So it's an external way to estimate, because there's no other way from which you can estimate this value. So this gave a very good method of estimating. So which means there was a second phenomenon which was shown, and it did prove to be a good one. Again, what was the problem? The problem was a change in the sign of the Hall coefficient. We all know if I'm going to do a Hall coefficient for the case of a semiconductor, which is an N-type or a P-type, your RH RH is going to change from -1 by Ne to RH. For the case of a p-type semiconductor, this comes to 1 by Pe. So this is something which was not understood using the Drude's model. Then the third concept was the thermal conductivity, where you have what is called as the Wehrmann-Friend's law. What is the thermal conductivity? Similar to the Ohm's law that you do in a transport. When there will be a thermal current which will be carried by the free electrons. For a small temperature gradient, I can find out what is the current density in this case, defined using the thermal conductivity here, and the ratio of the thermal to electrical conductivity, which you have read as Wehrmann-Friend's law, was proving to be correct. So everything was very happy at this point. Everybody was happy at this point. But finally, what they realized is that there was some error in these calculations which were there. There were two errors which were made, which compensated and then made us all happy, saying that Wehrmann-Friend's the law which was there was quite correct. The reason being, the estimation of your specific heat capacity here had 100 times smaller value, and for the case of the velocity had 100 times larger value, as a result of which what you could see is that this formula proved to be extremely correct. Why was this happening? The reason is the result was inadequacy in the classical statistics. The classical statistics which were used to deal these free electrons were not sufficient enough to explain three fundamental properties. One is the variation of conductivity with temperature. That is, your sigma T could not be explained. Okay, you could not explain sigma T as a function of temperature. You could not explain RH. Why should it go from a negative to a positive value? And third one is, of course, the case of a thermal conductivity, where that is your specific heat is something which was questionable. So what was the next step? The next step was, by this time, what we had was the Pauli's exclusion principle was in, and we had to make use of these to really look at how these electrons are going to behave, which essentially means I'm going away from the classical theory to a quantum theory and including your Pauli exclusion principle. Now, what is it that we are doing here? If you see here, I have shown the Maxwell-Boltzmann statistics, where at different temperature, this is talking about how the velocity is distributed for the electrons for a given temperature. So what you can see is the velocity is definitely changing as I'm going to increase the temperature. This is what your classical statistics says. But I am not very happy with this, because this is not actually helping me understand certain properties of my material, especially the one in case where spins are involved. How do I consider the electron spins here, which you have not done in the case of Maxwell-Boltzmann? So where you look at your Pauli exclusion principle and your quantum theory is helping us. So which means we are moving from a statistics which is a Maxwell-Boltzmann to a Fermi-Dirac distribution function, which I call it as a quantum statistics. So in summary, what I would like to tell is, what are the Sommerfeld theory of metals? We are considering a free electron theory. If you look at it, it is the same free electron theory you're talking about, where you're talking about that the electrons are free to move in the lattice is what you see, but you're looking at a Fermi-Dirac distribution function. Okay, so what we are going to see is, what is it that we are really going to do when you're going to look at the electrons in these metals by considering these two theories. Okay, I'll just move over to my slide. Just give me a minute. Yes. Yeah. See, what we are going to have here is, Just give me a minute. There is something which has happened.
No issue, ma'am. Take your time.
Yes. Yeah, yeah, I am. No, because I want to write the notes here. Yes.
Okay, okay.
So now what we are going to look at is, we are going to consider these electrons which are going to be free. As I told you, we are still working in with the free electron model, where I would say that, yeah. So we are still working with the free electron model, remember, in the case of the SOFIN. Now, but what are we going to do here? I need to work out how am I going to find out the energy levels. See, basically, you want to find out the energy levels available. Okay, so which essentially means I need to find out what are the energy levels plus occupancy of the energy level. See, what I want to know is, suppose I'm going to consider an atom's few atoms which are present. I really know that these are the energy levels which are available. Next is, here I'm going to talk about n number of electrons which are going to be confined in a particular volume. How am I going to fill up the electrons in these levels? So what I'm interested in looking at is the ground state properties of the electron gas. Since I put a free electron model, I'm still looking at the ground state properties of the electron gas. Okay. So when I say ground state properties of the electron gas, here I have to be very careful. I need to worry about at what temperature I'm going to look at. If I'm going to vary the temperature, is there any variation which is going to appear? Okay. So now let us say that I have n electrons. I have some volume which is present, which I have shown here also. Some volume which is present here of some length L, let us say. Okay, length L. Right now, for convenience sake, I'm just taking a cubic one so that my calculations can be easy. So I'm considering this volume. Let me say I'm having this volume in which my electrons are available. So I have put in here, if you see, I've written it as n number of electrons which are available in this case. So here I've written there are n number of electrons confined to a volume V. So what is my volume here? My volume V is going to be, yes, my volume V here is going to be L cube. So I've taken a cube here. So it is L into L into L. So I put this as an L cube here. Okay. Now again, I'm going to have an independent electron approximation, which essentially means electrons are not going to interact with each other. And when I talk, and I also use the levels are known used by Pauli. Now what is going to happen? I have a level which is present here. There is a particular rule which I have to follow. In one level, there can be one electron which can be present. But now looking at a plus or minus half spin which can be present here, this is the one electron state, but I need to look at the plus and half spin of the electrons. So what I would tell is, using my Pauli's exclusion principle, first I will identify the levels which are present, then I will start filling up the electrons in these levels. Now, how do you do? For which you must have done the basics of quantum mechanics, where you know to find the possibility or the probability of finding a single electron, I define a wave function psi of r, okay, of a single electron. So this is a three-dimensional case. Remember, I have considered a three-dimensional case because this is going to be important when later on we are going to look at the density of states, where we will reduce the dimension and look at what is going to be the variation in those cases. Okay, Yogesh, is it fine? Is it very fast or something?
No, ma'am. There is no queries. Please,
Yeah,
ma'am.
yeah.
Yes.
Okay, yeah. So psi of r of a single electron. So with one psi of r, I say there are two possible orientation of the electrons which can be present. So what you have put in is a Schrodinger equation for a single electron. This is something which you have done for any particle in a box. You must have done this for a three-dimensional cases where you are writing it in terms of your Hamiltonian and your eigenvalue here. Now the question is there any electron confinement? Okay. What do I mean by an electron confinement? See, remember, I'm going to have a very big room which is present with a lot of gas molecules which are available. Somehow, I'm able to move the wall of the room. What are you going to do? You're going to push the wall of the room so that the same amount of electrons are going to be available in a smaller room, where I would say there is sort of a confinement. So we are not looking at the confinement at all. What we are saying here is perpetually the electrons are free because I'm considering a large volume, except that this is going to act as a boundary. The edge of your edge of your cube will act as a boundary in this case. So which means I need to find out the boundary condition. My psi of r is equal to 0 at the boundaries of the cube. This is important for me. So which results in a standing wave solution, but transport a charge of energy by electron here. Now, this being a three-dimensional case, I need to look at the boundary condition in all the three directions, where I say that psi of x by z should be the same when my z is 0 or z equal to L. Or similarly, x equal to 0 or x equal to L, y equal to 0 or y equal to L. So this is what you call as a periodic boundary condition. What we are looking at is the way the Sommerfeld theory could move to find out what is going to be your energy levels. Okay. So now, what is this? We said that this is a wave equation is what we have to worry about. So what is the type of wave equation that you are considering? So your wave equation here is psi k of r is 1 by root of v. V is the volume, total volume. You are normalizing using the volume here, e power I k dot r. Now, you look at what had happened in the Drude's model, where you had talked about the electrons moving like a gas molecule, where you talked about the real space. Now here I am writing my psi of k in terms of e power I k dot r, which means I have moved from the real space to a momentum space in this case, which is a good one because we always deal with a reciprocal space in this case, right? Which is your K space, which you call it as, okay? Which has a relevance to your reciprocal space, which will help later on when you're going to do your band structures, right? So here, my energy right now, I'm writing in terms of Ek here. What does this mean? Look at this Ek. This can be obtained from my P, which is my momentum. And we will see about what is the speciality about this P here, which is h bar into K. So I can always write E is equal to P squared by 2m. And from here, I will get this is h bar squared, K squared by 2m. But remember, we are talking about a three-dimensional system. So I put my K squared as Kx squared by K squared plus Kz squared. Okay. Yeah. Of course, this is a position independent wave vector. We will see what is this. So my integral dr psi of r squared equal to 1, it only tells me that the probability of finding an electron within this bound volume V is going to be 1. Okay. Now, what is the significance of K? What we have done now is we have moved from R, which was the real space, to K, and we are trying to get a relation now. Why do we do this? We already know that the eigenstate of a momentum operator is what you use to solve your Schrodinger equation there, which is nothing but your P h bar into K. From where I can determine the velocity, which is h bar K by m, and E is what I showed you can get it. Okay. Now looking at what is the interpretation of K, e power I k is constant in any plane perpendicular to k and is periodic along the lines parallel to k. Let us forget about this one right now. We'll get back to this later on. Okay. My lambda, I associate this k to my de Broglie wavelength lambda, which is equal to 2 pi by k. And remember, we are also using a boundary condition because I said that at L, we are using this as a boundary condition because the edges of my cube are L in all the three directions. So I get EIKX into L, EIKY into L, and all the three directions, this is going to be 1. Okay? Which means my Z, X, Y, and Z, or Kx, Ky, Kz, I can write it in terms of an integer quantity. And we all know this K is not a real space. Now, this is a inverted space. Okay, your K is going to have a dimension of, what is the dimension of your K? Your K is going to have a dimension. Yes, this is going to be a dimension inverse of length. Going to have a dimension inverse of length, so which is 2 pi by L, and alpha x. What does this say? This is only telling me that I have discretized this in my K space. What I have done is I have moved from my real space and tried to find out discrete points in my K space. This is how we have done. So that gives me my quantization condition in the K space, where I say how many number of allowed states can be present. What is this? I have an energy E, that's what is your eigenvalue, which I have written here. And this, every energy is identified by a K point. So I have identified in my K space several points, which I call them as several energy states which will be present. And with this, now I am ready to fill it up with the electrons. So what have you done? Right now, what I have done is I have tried to find out how many number of energy states can be available by looking at what are the K points. So how did you come with these K points? Here I've just shown a two-dimensional graph here, where you can see that depending on what is going to be the size of the cube that you have started, I have identified the K points. Okay, here you can see along the X direction, since we have considered a cube, which was L and L and L, L into L into L, you see along my Kx here, this is going to be 2 pi by L. Along Ky, this will be 2 pi by L. So every point I can find out what is the area, and in a 3-dimension, I can find out what is the volume. So 2 pi by L, so which means I had a volume V in my real space. Here I am going to have a volume 2 pi by L. The whole cube is going to be the volume in my K space. Let me put it as Vk here. Yeah, so this is going to be my volume in my K space here, which is 2 pi by L, the whole cube. Now, the volume in K space, that's what I put it as Vk, will contain how many number of points is the question. Okay, so now I have identified what is going to be the distance between each of these K point in my K space. Now I would like to get the K space density of levels. What does it mean? How many number of levels are available in my K space is what I'm trying to count, which will be V by 8 pi cube, because I've considered your sigma, which is going to be the volume in the K space, divided by 2 pi by L. What is 2 pi by L? Which is going to be my Vk. That will be nothing but sigma of V, which is the volume in the real space, divided by 8 pi cube. So what you have got is a K space density of levels in this case. Now, how large is the K space? Now you look at this expression. E of K, which we have written here, which is h bar squared by 2m into K squared. So if I try to plot this, how is this going to look like? Let us plot this. If you look at it, this is nothing but a parabola. So take this as K and this is as E, and what you will get is a parabola here. Now, if you look at it carefully, I have not put any condition on the K. What should be the extent of K? So what does it mean? What I have done is I have found out levels. These are energy, the possible energy levels. See why I keep on telling the possible energy level later on when you are looking at a transport. Even if you have electrons with you, if you are
Excuse
not
me, ma'am.
having the, yeah,
Sorry for interrupting you, ma'am. There is a question in chat box asked by
yes,
Veera Pandian. He's asking what is the difference between energy states and density of states?
no, I will get to density of states is going to tell me, I will be doing the density of states. After you decide what are the energies available, after you fill up the electrons, you are going to find out how many number of electrons can be available between an energy E and E plus D. Basically, how many number of energy levels are available for occupancy between an energy E and E plus D. That is what your density of states is. Okay. Here, what we have done is
The screen
we
is
are
not
trying
visible.
to put, yeah,
Ma'am, your screen is not visible.
yeah, yes, I'm coming
Yes.
to it. Here now, yeah. See, that's what. We will go to the density of states. Okay. Here, what I am saying is I am trying to identify the energy as a function of K with a question: what is the limit on K? Right now, with no other value of variation in my Schrodinger equation here, I will see I have not put any limit on my K. Later on, when you are looking at semiconductors, where what you will see is, rather than talking about the electrons which are freely moving, I would say that the electron is going to be present in a lattice. The periodicity of your lattice will come into picture. When I add that, that is going to put a condition on my K, what you call it as a zone boundary. So right now, for the case of the metal, I'm not even going to consider all those things. I'm only saying that my E of K is continuous here in this case with no limit that I'm going to put on this one. But the limit is going to be decided by the volume that you're going to consider. So in general, if you see, the value of the number of K points is of the order of 10 power 22. So what we have done is, we have identified the levels. Now we have to fill up these levels using the N electrons. How am I going to fill up these levels? What I would say is, every K point that you're talking about, every K point, I would say that can be filled up with one electron, one up electron and one down electron. So we are going to use the Pauli's exclusion principle. So what we have done, we have decided the available energy levels, and now we are going to use these available energy levels to fill up the electrons. Okay. Now, how am I going to fill? Can I simply keep adding my electrons and say that the energy of my electrons are going to be infinite? No, there is no possibility. So what I have done is, I say that I consider free electrons and I consider the energy levels. Next, I am going to, how I'm going to fill. Basically, what this is going to be is, I'm going to have these, yeah. So what you're going to have is, you're going to have energy levels which are going to be present here. And now I want to fill it up with electrons. This is what I want to do. I want to see which energy level can this electron occupy. So there comes this statistics which we are going to use. You remember, initially I did mention that we had used a Maxwell-Boltzmann distribution function for the Drude's formalism, where I identified an average energy. But now I'm completely moving to what I call it as a Fermi-Dirac statistics, which are used for electrons, those which are going to have a half spins or 3/2 spins, etc. Okay, a Fermi-Dirac distribution function, which tells me clearly that this gives me a limitation on what can be the energy up to which I can keep filling up the electrons. How is it? So I have these energy levels which are present here. So let me say I keep filling up with one up spin, one down spin, up spin, down spin. The question is, how much can I move? Can I fill up all these electrons in all the energy levels which are available? No. Along with this, I need to put my Fermi-Dirac distribution function, which tells me very clearly, I have this probability, my FD statistics tells the probability is 1 here, and after a certain value of energy, you will see that there is a 0 probability. So I have a condition which has been put by my Fermi-Dirac distribution, and this is what? This is at T equal to 0 Kelvin. So it tells me, no, you might have any number of energy levels which are present. My electrons are going to occupy only up to my EF, not beyond that. From this distribution doesn't allow me, or this statistics doesn't allow me filling up of the electrons beyond EF at 0 Kelvin. Okay. Now what happens when I'm going to increase the temperature? When I increase the temperature, what I will see is that depending on what is going to be your value of Kb into T, is that energy, what I will have is some of the electrons might move to a higher energy level. So this is going to be some kBt. What happens? So there will be available levels here. There will be some levels which are also being occupied. This is what you say. So from here, what you're seeing is beyond E greater than EF, you're seeing an occupancy for, yeah, E larger than EF, you are able to see some amount of electrons which are present. So what have we done is, we have now found out the available energy levels and the possible occupancy of the electrons in these available energy level with a condition of my Fermi-Dirac distribution function. Okay. So with this, we should be able to find out, yeah, this is what I've written here. So the number of allowed values of K with the, what I have done here is, I have put here as a EF, which is a constant energy, which I call it as a Fermi energy. Now, what is the significance of this Fermi energy? See, right now we were talking everything in K space, and suddenly we talk about a Fermi energy here. Is there any relation between this and the K space here? Yes, of course. What it does is, it is now putting a limitation on my value of K. So corresponding to my EF, I am going to have a value of KF. Okay. Then for simplicity, let me consider that these are points in the K space which are available. So what I want to tell is that since I have put a condition on my EF, I'm also going to put as a condition on my KF. And for the sake of convenience for calculation, what you do is, see, since we have seen there, the number of K points are very high, as high as 10 power 22. So what I'm going to do is, from a cube which I started, I'm simply going to look at a sphere. Okay. What a sphere, I'm going to consider a sphere in a three-dimensional K space where the radius of the sphere is Kf, which corresponds to my Fermi energy EF in this case. So what would be the volume? What I call this as a Fermi sphere. This sphere which I have put here, yeah, this is my Fermi sphere which I call. Are you able to see? I'm writing it small. Yeah, this is a Fermi sphere which I call, which has got a radius of Kf. So what is going to be the volume of this Fermi sphere? You remember we did a volume in a K space. I'm trying to look at that volume here, which is 4 pi Kf cubed by 3. Now, this Kf corresponding to EF. So I should find out the number of allowed values of K with the sphere. What is the number of allowed values? So my allowed values, I said, I have to divide it by my volume in my K space. So it is sigma divided by 8 pi cube by V. This is what I have done. And since my sigma is nothing but K pi F cube by 3, and this is the volume here, So what you will see is the number of allowed values is going to be kf cubed by 6 pi squared into V. But I also know that each k point can be occupied by an electron with an up and a down spin. So I need to put this number counting. See, as far as transport is concerned, I will not be worried whether my electrons is going to have an up spin or a down spin, because this quantum number is going to be important when I am going to deal with other properties. For example, when I'm looking at the magnetism of a system, now I need to worry about, when I talk about the occupancy of the electron, how many are up spins or down spins, that is going to play a role. As far as transport is concerned, now, remember later on when you are going to talk about a spin transport, these cannot be neglected. Right now, we are only looking at the transport of the electrons, where I only worry about the number 2, but not for the up and the down spins in this case. Okay. So if there are n electrons, so what are we going to do? I want to find out, given the energy levels, given the number of k points, I need to find out how many number of electrons can occupy all these k points. So that is what I write. In real space, when we started with n electrons in a volume V. I want to find out the number density of the electrons, which is n by V. So I can use this expression here to find out n by V, which is kf cubed by 3 pi squared. You remember when you did the Drude's theory, where you looked at the conductivity, you determined the value of n. Okay. Now here what I am doing is, if I know what is the metal which I am using, and if I am aware of the value of my kf, which I can, you will see how to determine the kf. What you will see is I can determine the number of electrons which are present there. Remember, you should also remember one thing, that this kf which I am writing here at 0 Kelvin, all the k points below this kf is all occupied. This is what I have written. At 0 Kelvin, k less than kf, all are occupied. Okay, which is not true when you are going to vary the temperature. So now what have we seen? Okay, what have we seen here? We have found out different parameters by going into using a quantum statistics and the free electron theory. We found out that there is something called as a sphere of radius kf, which is corresponding to a Fermi wave vector, contains occupied 1 electron levels in the Fermi sphere, which essentially means the surface of the sphere is a constant energy surface, whose energy correspond to your Fermi energy. So this surface actually separates your occupied and the unoccupied levels, and these are going to be helpful for metals. Remember, here we have done, because later on you might be looking at the Fermi surfaces. It is not necessary I will have a spherical Fermi surface, because in many of the metals where experimentally it has been seen that the Fermi surface is not a spherical one. I mean, this is a cyclotron resonance experiment, which tells that it need not necessarily be a spherical surface, because experiments can be done with 3 direction, and there is a huge amount of anisotropy which is present in this case when determining the Fermi surfaces of the metal. Okay, then you talk about the Fermi momentum here, h bar into kf. Once I have decided what is kf, I can find out my pf here, and since I know the relation between the energy and kf, I find out the Fermi energy and the Fermi velocity pf by m. For a classical gas, you look at the classical gas, when you did your Maxwell-Boltzmann, we found that is 3 kf t by m power half is the classical gas velocity in terms of my kf, which we have written here. Okay. Now, another parameter you can find out is what is called as a Fermi temperature, which actually does not play a huge role unless you're looking at some sort of lattice dynamics and other parameters in this case, where a Fermi temperature is also important. Once I know what is my Fermi energy, I should be able to estimate what is my Fermi temperature. and the mean free path, because when we started about the Drude's model, we did talk about the mean free path. Here what I do is, there I took the average of my velocity from my distribution. Here, since I've identified my energy, I can also identify what is going to be the maximum velocity of the electrons. I use this Vf into tau to get the mean free path of the electron. So once I can determine my Kf or Kf, from there I can determine the Ef, Vf and the mean free path in this system. Is it clear till this point? Is there any question?
Yes, ma'am. There is one question from Swati. The Fermi temperature is too high. What is the physical significance of such high temperature?
Is my video coming?
Uh, no, ma'am.
Stop. I started the video.
No, ma'am. Your video is not visible, but
It shows my camera is on here.
okay.
Yes.
Yes. Now it is coming.
Yes.
Yes.
Yeah.
Yeah.
Give it somehow,
Yes, ma'am. It takes
Yeah.
some time, I think. Yes. So, ma'am, there is one question in the chat box
Yes. Yeah.
asked by Swati. She's asking, the Fermi temperature is too high. What is the physical
Yes.
significance of such high temperature?
That is why I was telling that though we always talk about a Fermi temperature, in fact, if you look at the temperature of this thing, these are almost going towards your melting temperature. So you really do not have much of a significance of this temperature at all. Okay, it's too high. You're correct. You're correct, Swati. Fermi temperature is going to be very high because when you look at the metals, you have your Fermi energy something like 3 electron volts to 5 electron volts or 8 electron volts is the maximum you will see. You see the temperature is going to be too high, which is almost going to the melting temperature of your metal. The significance is right now not there, though what you will see is when we are going to talk about trying to get the other parameters like energy and specific heat and all that, you are going to talk about a temperature. When you're going to say that you're going to work at different temperatures, you would like to see whether you are going near your Fermi temperature or very low compared to your Fermi temperature. It is there that it is being used, or else, I mean, it is generally not a quantity which is physically used anywhere. Okay, fine. Basically, some approximations are to be made, and you're very happy to say, yeah, my temperature is very small compared to TF. Then it's easy to solve the problems. You will see that when you're solving the problem, you'll find that out. Okay. Yeah.
Ma'am, your video is not properly visible. Uh,
Yeah. I'm not properly
okay,
visible. I don't know. Yeah, I don't know why
Yeah.
this is happening.
Okay, it's
Even
all
I
right,
can
ma'am.
see my head is chopped off. My head is chopped off, partly.
Yeah, ma'am, tomorrow you log in from 2 devices. One should be your phone, the other one should be iPad.
Yeah, I will know. I will do with my other laptop. I will do that. Yes, I will do
Then
that.
we can see your
One
face
I will.
from one device and your talk from the other device.
Sure, I'll do that.
Ma'am, you please continue. You please continue. Saurav will join only at 6:15, not beforehand. I told him you will take 1 hour 15 minutes, and if you want till 1 hour half an hour more, then you please tell me. I will inform him just now.
Okay.
Ma'am, there is another question from Dinesh Singh.
Yeah.
The last time a diagram show between conductivity and temperature for metal. Please give idea
Yes.
about for 2D, 1D, 0D resistivity.
Yes, we will do. When you're going to do the density of states, I'm going to do all that. Okay. We'll first, for that, we have to move to the density of states, because there what will happen is in a 1D, right now, if you saw that we considered a volume, we considered a volume. Is what we did. We considered a volume which was very large, okay, in all the three direction. So I put one question there. I don't know if you looked at it. I said, is there any confinement, was the question. So I said that if I'm going to consider this complete volume, I had posed one question: are there going to be confinement of electrons in this particular volume? For which there was an answer which said, no, I am not confining the electron. The electrons are going to move around a bigger volume, is what I have told. But when you're considering a 1D, 2D system, there you're going to have a confinement along a particular direction. Especially if I'm going to do a 2D system. If I'm going to do a 2D system, what I will see is I might consider a dimension along my Z to be small, very small. So there is a confinement of my electron here, but a freedom for the electron to move along this direction. So what will happen is my energy level, which I am talking now, will not remain not the energy levels, the occupancy of the electrons in the energy levels, I have to redefine that depending on in what direction it is confined and in what direction it is free to move. Because once I'm going to talk about a confinement, depending on what is this thickness, okay, my Z thickness. If it is going to be in a nanometer scale or a micrometer scale, what you will see is my energy, which I'm going to talk about here, is going to become discontinuous. Okay, so there my transport, I have to relook at the transport that is occurring in such type of a system. Yeah, we will get to that. When I'm deriving the density of states, this will be clear to you. Yeah, fine. So I will go ahead with the next one. Yes.
Yes, ma'am.
Having done this, yeah, I need to find out what is the energy density of the electron gas. I want the total energy of the electron gas divided by the volume, which I can simply use my E. This is nothing but my E. What you are having here is, yeah, this is going to be my E here. Okay, dk into E of k is what I have done here for k less than kf. Why k less than kf? I'm only saying that it is 0 Kelvin. So I've looked at the energy density. So I can derive the expression of the energy density of the electron gas. But I also want to know what is the energy of one electron in the ground state. Okay, I still call it as a ground state because I'm still dealing with a system which is at 0 Kelvin. Yes. Okay. So N by V is kf cubed by 3 pi squared. We already derived it earlier. And E by N of one electron is going to be 3 by 5 EF. So what have I done? After identifying what is going to be my Fermi energy, I'm able to determine what is going to be energy of one electron in the ground state. So this is something which you can do given your dispersion relation. Now, let us get to what is it. This is what I call it as a dispersion relationship. My E of k, where I'm writing my E in terms of my k, which is nothing but the k space values. Okay. The question is, will my dispersion relationship always be like this? Not necessary. I can also have metals which can have a varying dispersion relationship. In fact, yeah, you can see some of the questions which you see in net where you get a dispersion relationship, not necessary in this way, but it might be some sinusoidal or a cos of k into a or something. There again, you can try to plot your E versus k graph using a different relationship. But remember, if I'm going to have a cos of Ka, what I'm going to have is a periodicity which will come into picture, which I'm not getting into right now. Okay, I'm only dealing with the case where I can draw a simple parabola between my E and K. Okay, so when you do that, you can also find out my E of N is going to be 3 by 5 because E of F KB into TF is what I do. But this KB into TF is going to be a very large value in this case. So one can look at a problem. Once I know the energy, there are certain parameters you can work out. If I consider a metal is going to have so much amount of electrons which will be present. If I try to estimate my bulk modulus, that is going to be huge. Look at this. The pressure is given by 2 by 3 E by V. I put it as a problem. Let me see if we can work out this problem also. Pressure of the electron gas can be determined by 2 by E by V. So since I know what is E by V from this expression, I should be able to estimate the pressure. Once I know my value of Kf, try to see what is the pressure here. The pressure is going to be too huge, which you can't even imagine, because the high density of electrons which are going to be present in the metal, and the bulk modulus again, which is going to depend on small n. We know the order of n is going to be something like 10 power 28 electrons per unit volume is the electron density which you are going to have. So this is also going to be huge value. Okay, so right now what I have done is, please, I've also given this book, Sommerfeld Theory of Metal, Solid State, Ashcroft and Mermin. Please go through the first chapter very nicely. You can try to understand your second chapter only if you're very clear with your first chapter, which is nothing but the Drude's formalism, where he talks about each of these transport and thermal properties in this case. Yes. Now what have we done? What we have done here is we tried to find out what is the number of K points. Okay, it is basically in real space. It is basically what I am having is slabs which are the square slabs which are present in a room, where every slab you say that I can fill it up with electron. So I counted the number of slabs which are present. Okay, and I have n number of electrons present with me. I have tried to see how much of electrons I can put in each of these slab. But here my condition or my maximum energy is decided by my Fermi Dirac distribution. So this is what we have done. So having done this, the next question that we have to worry about is, suppose I'm considering my Fermi Dirac distribution not at 0 Kelvin, but at some other temperature. Okay. So this is a temperature greater than 0 Kelvin. Okay. So now what happens is, I need to find out between given two energies, how many number of electrons are present, because this is going to be important for me when whether I'm going to consider a 1D, 2D, 3D systems or a zero dimension system. Okay, my G, which I call it as density of states, as somebody asked me, FD and energy, this is going to be my EF here. Okay, as somebody asked me, what is the difference? Right now what we did was a number counting, but if I am going to have E, between E and E plus DE, I want to find out the number of electrons which are occupying this, or the number of levels which are present here. Or in other words, since E is related to K, I can say between K and K plus dk, what is going to be the electron occupancy or number of levels. See why this is important. I told you that when I'm going to talk about the transport of the electron, for me, I need to have the levels available for an electron to move in whenever I'm looking at a transport. If suppose I have less number of electrons and more levels present, the question is, can these electrons really occupy these levels? Or the other way, I have electrons, but I don't have the available level, then what you will see is there cannot be any electron transport which will take place. So which essentially means I need to find out for any given temperature, how much is going to be the number of levels which are present between E and E plus DE. So that is what I call it as a density of states. So what do you have? This is, we say that the electrons are free particle confined by a potential here with all these boundary conditions. We forget that. So I want to find out what is the number of quantum state. Just now one person asked me what is going to happen in the case of a 1 dimension, 2 dimension, and a 3 dimensional case. So let us look at the density of states first for a 3 dimension. Okay. So what you're having is the number of quantum states is what you're going to count between interval k and k plus dk, or between e and e plus dk. This is what I have done here. So how do I do? So I have my k points in my k space. I'm going to consider a small element dk in this case. Remember, every point of your k space is decided, or your volume in the k space is decided by your bulk L that you have considered. Okay, so please keep this in mind. If I am going to go for a 2-dimensional system, what will happen is I am going to have a kx. So let me say that there is a 2-dimensional system, and this is going to be my x, and this is going to be my y, and along my z, okay, this is going to be a very small thickness which is there, basically graphene. Example is a graphene sheet. I take a small sheet of graphene. Okay, what is a graphene system? It is something which is having a, yeah, maybe in the next class I will show you this, which is going to be a sheet which contains carbon here. These are carbon atoms which are present. So I'm just going to have a single sheet of graphene. That's the best example for a 2-dimensional system, where you see that you're going to have along the 2 direction, my electrons are free to move. Along the 3rd direction, it cannot move. So it is confined along my z direction. So here, when it is going to be confined and all, remember when we took this L, L, and L, which I have written, I hope you are able to see. Yeah, this L corresponds to the real space box which we have considered. If this L becomes very small, what should happen? My 2 pi by L is going to be a large value. Okay, you appreciate this. If my L is going to be very large, my 2 pi L is going to be so small. If L is going to become very small, which means a small distance here, my 2 pi L is going to be very large, which means the distance between k points are going to be larger. Now you should imagine what is it that is happening. As my distance is going to become larger, okay, I told you that you have a number of k points which is 10 power 22. Now, with my dimension in my real space becoming smaller and smaller, what you are going to see is that the distance between every k point is going to become larger. So the number of k points is going to become lesser, which means I can treat it as a system where the discreteness has set in. So this is what will happen. So I am going to have a transport which is going to be cleaner on 2 direction, whereas on a 3rd direction, what I will see is this cannot be the same. So which means when I'm writing my E of k, okay, where I wrote my k is going to be kx squared plus ky squared plus kz squared, what I will see is I can say my h bar squared kx squared plus ky squared by 2m, okay, plus in the other direction, now I will put it as nz, where n, I can write it as what is n. This is, okay, let me put it m. Don't confuse it with your density there, where m can be 1, 2, 3, etc., which means there is a discreteness which has set in. So along the dimension where you cannot allow the electrons to move so freely, you have put in discrete levels. So only along my x and ky, you are seeing that there is a continuous one, not along my z. Okay. What you talk about in the real space is, in the real space, my electrons are freely moving along the x and the y, whereas in the z direction, I have put a boundary condition where my thickness is it is so thin that I will only look at discrete levels. So this is what is going to affect your transport. For the person who asked about what will happen if my dimension in other direction is going to be smaller, the same will be the case if I'm going to consider the case of a rod. Suppose I consider a rod, and this is going to be, say, a nanometer scale. and this is going to be a length which is going to be large compared to this diameter here, suppose micrometers or in millimeters, then what you will see is the electrons are free to move along my L, but it is confined along my this direction. Across this area it is confined. So then accordingly what will happen is discreteness in my K points will set in along that direction, whereas it will be a continuous, your parabola is what will be decided along in one of the direction. Okay, so this is what. Should I stop now or what? Hello? Hello?
Yes, ma'am.
Ma'am,
Yes,
how
ma'am.
much?
Yes, ma'am.
Yes, ma'am.
Has Dr. Saurav Sur
Yeah,
joined?
so because
No, ma'am. He's not
Just
in
one
the
second,
list.
checking.
yeah, because I have to start my
Yes, ma'am. I
density of
think he has
states. I
joined.
thought now I cannot, it will be halfway if I'm going to do this.
Yeah, yeah. It's okay. Okay. Yes, ma'am. Yes, ma'am. Dr.
Yeah,
Saurav, have you
so
joined? Hello. I think he's joining with the other device also. This one must be his laptop
And
where.
there is a name. There is a name in the list. Saurabh. I
Yes,
think.
yes. 1 minute. I'm calling him up. Yes, ma'am. I think he would be joining.
okay. So I
So
will
if there are
continue
any
with this
questions,
tomorrow.
if there are any final
Yeah.
questions, you can take them up.
Yes. I will just see.
Dr. Yogesh, please see if there are any
Ma'am,
questions.
there is no more question in the chat box as well as in the YouTube. Yeah, ma'am. There is one question come.
Informative, please give about this. We will come to this question
Uh,
is yes.
yes, ma'am. There is a question from
Density of
Dinesh
states
Singh.
for zero dimension. Yeah, for the case of a zero dimension, what you will see is you will see discrete energy levels. You will see discrete energy levels in this case. In the case of zero dimension, in all the three direction, you will see that your kx, ky, kz, because you're going to have a confinement of the electron along all the three directions. Okay. So
Okay,
we
any
do
other?
the density of MAM for curved 2D shapes like Buckminster Fullerene is a confinement condition, same as no. For a, see again, the confinement, when you talk about a confinement, when I say quantum confinement, it is going to depend on what properties you're looking for. The confinement effects, is it changing my transport behavior or is it changing my optical behavior, is going to depend on several length scales. Okay, so I think when if we talk about a nanometer scale, there we can say that there are several length scales involved. For example, one of the length scale we talked about is the mean free path length. Okay, if my mean free path length is matching with my nano size, then what will happen is your transport is going to be entirely different than what you see in the bulk. So when you take the case of a Buckminster Fullerene, when I say quantum confinement, I have to worry about what is it you want to study in this. For example, if I take the case of a metal system, I will not see a confinement till I am going to reach something like 3 nanometers or 2 nanometers. While on the other hand, when I'm going to look at the semiconductors, maybe even with the 20 nanometer sizes, I might reach a confinement. So this confinement condition is going to be based on several length scales. When I say several length scale, there is something called as a charging length scale. The e-charging of quantum dot is there. So it is going to depend on that also. Okay, so these are all interesting properties based on what applications you are looking for. I need to look at which length scales I am going to deal with when I'm going to deal with these systems. Okay, yeah. So I think I will see you tomorrow with where we will derive these density of states and we will look at some of these problems. Okay, fine.
Thank you, ma'am. Thank you so much.
Yeah.
Thank you so much,
Okay.
ma'am.
Okay.
Thank you so much. We
Okay.
shall see you again
Thanks
tomorrow.
a
Thank you so
lot.
much.
Thanks a lot. Thanks a lot.
Should I stop live recording, ma'am?
Yes,
Yeah,
yes,
please
yes,
do.
yes,
Yeah,
yes.
please.